So there is good and bad. Normally, if I'm teaching this class in a regular class, I like give that quiz at the end of the first day, just send them home. Worried about it, and then I tell them the next class that I was a diagnostic, so don't worry about it. But with you guys, I have to speed everything up. So you get to know, you have some relief right away. Don't have too much though, so some things to note. Right now, you should be able to see your Blackboard. So on Blackboard. So this is for our particular class, so you have to click on the Math 2009 LMSA. If you go to course documents there, you'll see the documents that I posted for the class. So at the moment, you can see the syllabus there, the same one that I handed out to you in case you lose a physical copy. Two other important things I want to also mention. You have folders there. One perhaps immediately relevant is quizzes and quiz answers. So right now you'll see quiz 1 is there and quiz 1 answers are there. So it came live after you guys finished. Don't look at the answers yet, I'll talk about that. I'm just informing you at the moment. You'll also see, I believe that the folder is called Class Handouts. So in addition to recording the lectures and giving you notes that I'm going to be writing on the board, I actually typed out notes for the class. They can kind of think of as the guidelines for each of the lectures. So you'll see the actual notes for the first 3 sections. So there's chapter 0, what we're going to start with, which is preliminaries. And I believe 1.1 is the equation of the line, and there's something else there. But I do actually give the typed up versions of the notes. So if you go there, you'll see the first one looks like this, which is the basics that we're going to go over. And I list the examples that we do. Of course, they're not worked out. I work them out in class, and we work them out together in class. But you'll see the notes for everything I'll be teaching. You'll find in course handouts, right? And later on, other folders will appear like test reviews and tests and solutions. So usually when I post the quiz, I'll post both a blank version and an answers version. So you can go back to the blank one if you want to do practice or something like that, and then you can check your answers afterwards. A common error that I see students make, that's actually yes. You have to be aware how to use the solutions. I'll talk about this more as time goes on. There are 2 ways that students fool themselves into knowing something that they actually don't know, and then when it comes to a test, they are surprised at how they do. One thing is misusing solutions. So a lot of students, they do bad on a quiz, and what they're going to do, they'll immediately want to look at the answers to see what did I go wrong, did I do da, 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 da. That is the wrong thing to do. I know you will want to do that, it will be a natural tendency. You are shooting yourself in the foot by doing this. You need to use solutions sparingly. Right? Meaning, before you look at the solutions, even to the first quiz, it is better for you to go do over the blanks first. So say you don't feel good about a quiz, you feel like you bombed it, don't immediately look at the answers. Print out the blank version of the quiz and go over it slowly in an environment where you're not under time pressure. Go through it slowly and see if you can actually do it on your own. So I would untimed, but no help. do as much as you can do in that scenario. Now if you realize you're still getting stuck, you now use notes to help. If you still can't figure out the answers from going to your notes, now tutoring. Go talk to somebody, set up a study group. And then you look at the answers. So in your tutoring session, when you're working with the tutor, you can say, I tried this on my own, I even looked at my notes, here's where I am, help me, right? That is the first time you should be looking at the answers. Looking at it any earlier, you risk kind of tricking yourself. Because sometimes, especially with the test, when I actually show all the steps, hindsight is 20/20. So a lot of times when you're reading a solutions, it'll make sense to you once you see the steps laid out. You're gonna, oh yeah, that makes sense that that's what it is. But coming up with those steps by yourself is a completely different thing, right? So you'll read a solution and you'll be like, oh yeah, I get it, but you really don't get it, right? The person who wrote the solutions get it, and you just kind of, in hindsight, understand what they did. Right? This also happens a lot when in class. So people will be like, oh, I come to class and I understand everything. Again, if you're watching me do something, it is very different from you doing that thing. Right? You need to prioritize doing things on your own without help. You want to help, you should get help, don't get me wrong. I'm not saying don't learn to do it on your own. You should get help, but only after you put in a fair amount of legwork. Right? You should prioritize doing problems on your own. The best scenario is to do it under test conditions. So when you're practicing for a test or a quiz, you should actually, and you think you've studied enough and you think you understand the problems, you should actually time yourself and give yourself a clock and pretend it's a test and try to do it all in one sitting. So under test conditions is the very best. So you want to always be modeling the scenario you will be under when you're taking the test, right? And again, even if you're studying and you are getting through things on your own, but you're taking forever to do it, you're kind of half watching Netflix or you're kind of doing this, again, when you come to the class and Jhevon says 15 minutes left, it's a very different scenario. You're in a very different headspace, right? Your brain is going to be releasing all sorts of chemicals that it wouldn't have released otherwise, and it's going to mess you up. So you really want to prioritize doing things on your own. Don't just go straight for the solutions. You want to use them sparingly. And it will also give you a good idea for when you do get help, you'll know exactly what you need help with, right? Some people go to tutoring and they're like, I need help with everything, I don't understand everything. That's not very helpful, neither to the tutor nor to you. But if you put in a fair amount of work, you'll be able to pinpoint exactly, I'm getting stuck at this point, I don't understand this thing, and your brain will automatically learn the material much better because you're attacking it from so many angles. By the time you actually go to tutoring and get help or see solutions, yes, that everything is going to fall into place. So you don't want to start studying out of order and doing things prematurely, because it'll actually, a lot of the times it'll trick you into thinking you understand something when you don't. So yes, the answers are here. They would not be the first thing I look at. I would go back to the blank. So if you feel like you did horrible on the quiz I just gave you now, don't look at that, look at that, right? It's also, I think, a good, since we're in this class, probably a good idea is that to go over the blank version in the recitation session. And maybe I'll make sure that your recitation instructor has access to the Blackboard, so maybe she can look at the answers and guide you guys as well. But yeah, you can probably even start out your recitation session by going over this quiz and being like, okay, trying to figure out where you had trouble and maybe fill in some gaps here. But yeah, so our Blackboard is now live, you should be able to see it. I'm pretty much posting everything you'll need under course documents. And there's something else, there's another section in the side menu bar about getting my MATLAB stuff, so you should be able to see it there. But as for what I'll be posting them under course documents in this Blackboard. And right now the syllabus is there, the quizzes are there, and the first 2 class handouts are there. So be careful how you're using answers and be careful how you're actually practicing. You do want to practice for what you need to be able to do. Just watching someone else do it is not going to cut it. You're not going to become a great basketball player by just watching Michael Jordan. You actually have to go on the court. And at some point you need to play some basketball, right? You can't just, oh yeah, I saw how he slammed dunk that. It's very different doing it on your own. Okay. And like I said, the first quiz diagnostic, but it should be instructive of kind of where you want to be in terms of algebra. But let's actually continue. So I know you guys don't have this now, but in general, you can print out the notes ahead of time, maybe bring it to class, but at least try to work on these at home ahead of the class. If you don't get 100% of it, that's fine. Just get your brains working on it. Because one thing, if your brain gets tired, you'll tend to kind of zone out and skip out. It's going to happen anyway. But if your brain is already familiar with the material, it's familiar with the examples I'm going to be looking up, it's much easier to stay engaged. It's not being taxed as much, so you won't get tired, mentally fatigued as quickly. So that's also a good idea. So, I mean, the first class you won't have this. But in general, I will be posting the notes for the lectures before the lecture, so you can print them out, try to work through most of them. And then when you come to class, you know exactly what you need to pay attention to, and you can almost ignore the rest. Yeah, so this is chapter 0. Technically, it's not a part of our syllabus, but I think there are a lot of important lessons here that we need to make sure that we have down, a lot of skills that we will be using as time goes on. And I just want to make sure that we're all on the same page, so we're actually going to go through chapter 0. These are the preliminaries. So basically this is going to be like basic arithmetic, algebra, things like that. First thing I want to make sure you guys are very familiar with is the laws of exponents. So, if A is a positive integer, then x to the A means you're multiplying x by itself 8 times. But we can extend this function to work for other numbers as well, and we'll talk about, in particular, having fractions as powers. But in general, it can have any kind of powers, but the basis of it is we want to represent repeated multiplication by using powers. And so with this, we have some laws or rules. One is you should know that if I have something like this, if I'm multiplying bases of the same powers, what do I get?
A plus B.
X to the A plus B. You have to add the powers. Okay? And that's because this one is just x A times, and this one is x B times, and in total you have A plus B of them. Okay. So that's why when you're multiplying things at the same base, you add the powers. What about dividing? Right, you subtract the powers. Okay. And the idea is because you have this over that, you'd start canceling, and the amount of things you'll cancel is you'll have the A number of things, but you're getting rid of B number of things, and you have that. Of course, this assumes your x is not 0, because we can never divide by 0, so that's that idea. And A and B here can represent any numbers, not just whole numbers. Whole numbers is just kind of where it started, but you can actually do this in general. We have 3. What about x to the a raised to the b. Multiply the powers in that case. Right? You have a copies, but you have b of those copies is a times b copies of x. Or what is x to the 0?
1.
It's 1, as long as your x is not 0. And you can think of that, the reason why is because x to the a minus a, if I plug in a equals b here, that's just x to the a over a, and that's 1, but that's actually also x to the 0. 5. What about x to the 1?
X.
It's just x. Right? Multiply x by itself 1, not a big deal there. What about something like x times y raised to a power? Right. Powers distribute across multiplication. They do not distribute across addition. So if there was a plus sign here, I couldn't do that. With multiplication, we can. So powers actually do distribute across multiplication and division, which is what this rule is going to say. Similarly, if you have a division and you're raising to a power, that's just x to the a over y to the a. Another thing that you need to know. What does it mean to have a negative power?
Because it means
The reciprocal, 1 over x to the a. And that's again because you can apply the previous rules. This is just x to the 0 minus a, which we know is x to the 0 divided by x to the a, but we know x to the 0 is 1. So we get that. Get 9. What if I had something like this? A fraction in the power. Yeah?
It's a radical.
Radical of what?
Radical a over x to the b power.
This?
No, wait. No, x to the a, and the index is b.
Yes, the root is b, that is a. Now, there's a way that, back when I was a kid, I learned this, and I still say it in my head sometimes now. But it's called flower power. So every time I see something like this, I imagine a flower where the bottom is the root, right? And the top is the flower, which rhymes with power, hence flower power. So I know that the top number is the power, the bottom number is the root that's under the ground, so that goes on the radical sign. Now, in general, we can actually swap these, and we can interchange at will if x is greater than 0. If your x value is actually negative, there are some issues here. We'll talk about those when we get to domains. Because if the value of b is even, you can't have a negative under the radical. So this is the b root of x to the a. Common expressions. Square root of x. Now, when you see that, what that actually means is that there's a 2 here, but they don't actually write it. So this is one thing you need to know how to write as a power. What's that as a power? X to the 1/2. What if I had the cube root of x?
1/3.
X to the 1/3. What if I had the 5th root of x cubed?
3.
X to the 3/5. And sometimes one way is easier to compute than the other way. So another example here is if I had 9 to the 3/2. You can notice that there are a couple ways you can think of this. You can think of this as the square root of 9 cubed. You can also think of it as the square root of 9 cubed. Now one of these is obviously easier to calculate than the other. Like you wouldn't want to have to cube a 9, get a huge number, and then take the square root of that. It's much easier to just square root the 9 first to get 3, and then cube the 3 to get 27. Right? Especially if you're doing by hand, the order in which you apply things can matter, but you can swap them if it's greater than or equal to 0. Now, a lot of the rules that we'll be doing in calculus will be stated in terms of powers, so you should be able to convert things to power form. So a lot of times I'll give you something as a radical and you want to convert it to a power to be able to apply some rule that I have. So you should know how to do that. I think I covered that. I don't think I have to do any examples yet. But now I want to define some terms for you. First term I want to define is a term. So here's a definition. A term is a constant or a product a constant and some variable. So example, x squared, 5x squared are terms and if I look at x squared plus 5x, I can think of this as two terms. Right? So x squared by itself is one term, 5x by itself is another term, and I can add them together, I create two terms usually. And a combination of terms is called an expression. And by combination I mean a sum. An expression involving an equal sign is called an equation. For example, x squared plus 5x equals 7 is an example of an equation. These are terms. This whole thing is an expression. And this thing is an equation. Plus 8. An expression with one term is what we call a monomial. It has two terms. We call it a binomial. It's three terms. We call it a trinomial. What other expressions do I want to define? Okay, coefficient. And leading coefficient. term is called a coefficient. Example, in 5x squared, that the 5 is called a coefficient. In an expression, the coefficient of the term with the largest power or sum of powers is called the leading coefficient. I'm going to give you some rules that talk about leading coefficients, so I want you to know what I'm saying when I say that. So the leading coefficient is, for example, I can have 3x to the 7 minus 2x squared plus 4. And you should recognize that this 3 is the leading coefficient. It does not necessarily have to be in the lead. If I had 3 plus 2x cubed minus 7x to the 9th, minus 7 is the leading coefficient. It doesn't have to be in the front. It's just the guy, the constant, that's attached to the person with the highest power. We call that the leading coefficient. He can show up in any location. Oh, that's offhand. So far, I'm not saying anything crazy, right, everyone? This is kind of okay. Sometimes I'll go a bit quickly because I expect everyone to already be somewhat familiar with what I'm saying, but you can stop me if you have questions. Here's another definition. A polynomial in one variable. Those are the only ones we deal with in Calculus 1. Expression that looks like that, where the AI are constants, just numbers on the number line, and n is a non-negative integer. The expression non-negative means greater than or equal to 0. Integer means whole number. Example, sorry, plus 1. 3 minus 2x plus 7x cubed. 4x to the 4th minus 2 and 5 are polynomials. Non-examples. X squared plus radical x. Simply radical x. 2x plus x to the 1/2. 3 minus 1 over x. 4 plus 2x squared minus x to the minus 1 are not polynomials. Polynomials are expressions of this form. These are constants. The variables have to have whole number powers. So these are examples. This one has a radical. Radical is a half power. Same thing here, there's a half power. It does not follow the definition. 1 over x, there's a division here. There's no division there. Negative power here doesn't fall in line because there should be no negative powers. And that's very important. So you might have things that look almost like polynomials, but they're not polynomials, and they can actually be very different. So for example, anything I can plug into here and it will make sense, but not anything I can plug into here and it will make sense, and not everything I can plug into here will make sense. They'll have very different behaviors. So know a term, an expression, an equation, what a coefficient is, what a polynomial is. The degree. I'll also mention a theorem with degrees in it. The degree of a polynomial is the highest power that appears. For example, the polynomial 5 versus the polynomial 2x plus 1 versus the polynomial 3 minus x squared versus the polynomial x cubed plus 2x minus 7. This is a 0th degree polynomial, which is what by definition a constant is. Constants are polynomials. It just means you plug in 0 for all these numbers here and just leave the a0 number by itself. This is a 1st degree polynomial. We might also call it a linear polynomial. So if I have the phrase linear polynomial, I'm talking about something that looks like that. This is called a 2nd degree polynomial. I might also call it a quadratic polynomial. This is a 3rd degree. I refer to this as a cubic polynomial. Those are some very common ones. There's something also important. The idea of like terms definition. Terms are said to be like terms if they differ, perhaps, only in their coefficients. So if everything is the same except perhaps the coefficient, we call it a like term. For example, I wrote down a bunch of examples here. So these guys here are like terms. Why? Because everything, these are the coefficients. Now they're all different, but the part that's not the coefficient, it's all the same. So once you have the same thing that's attached to a constant, we say you're a like term. Now, otherwise you're not. So if you have 2xy squared and 2x squared y, not like terms. Even though they have the same constant in front, they both have x's and y's. The x has a square on it, the y has a square on it, and that one doesn't. So these are not like terms. These are unlike terms. That's what they're called. So like terms are just things that have the same, they're all the same except for the coefficients. Here. Let's do some math operations here. Adding and subtracting terms. We can only add or subtract like terms. Addition and subtraction does not work otherwise. So let's actually do some examples here. So the example is combine via addition or subtraction where possible. All right, okay. Slow things down with some calculations. A lot of notes here, but we're starting from the beginning, not taking any chances. Well, I took math 5 years ago, I don't even remember what a coefficient is. Now you know. You have no excuse. Okay, so how would this work? You guys can just call it out and then show you. What would you do here?
3x plus 7.
Right? So these are like terms. The coefficients are different, but they are attached to x's, right? There's an invisible 1 here. So those two are like terms. You can combine them by adding the coefficients and keeping the like term. So you have 1x, so you can even, so you have 2x plus x plus 4 plus 3 if you're into that rearranging thing. And this ultimately becomes 3x plus 7. That'll be the answer. B. 2x squared plus 3x cubed. What is that? Right, that's 2x squared plus 3x cubed. If you thought that was something like 5x to the 5th, you're way off. And yeah, you can actually combine this. It's a trick problem. Okay, x squared plus x plus 2 plus 4x squared plus 2x plus 1.
7x plus 3x plus 3.
Combine like terms here.
7x squared
7x squared
plus 3x plus 3.
3x
Plus 3.
plus 3. D. We have 5x squared plus 4x minus 1 minus 3x.
2x squared.
First you have to distribute. The fact that there's a negative sign in front of the parentheses, you have to do distribute here. So this is 5x squared plus 4x minus 1 minus 3x squared plus 2x minus 2.
2x squared plus 6x minus
Now you combine these, right? 2x squared
plus 6x
plus 6x
minus 3.
minus 3. So D requires something we call the distributive law. It is basically a law that says the following. So if you have a number in front of a parentheses with a sum in it, to expand that, we call this expanding. You take the number in front and you multiply everyone. This is called expanding. By the way, expanding is the opposite of factoring. So if you went here and you go to there, you say you factored. If you went from here to there, you say you've expanded. Now, you must follow Pemdas whenever you're trying to figure out what some arithmetic expression would evaluate to. It's just a way to remember the order of operations, as they're called. If there's any ambiguity in a calculation, you work it out by following the rules of Pemdas. Now, Pemdas is a mnemonic.
Did we do the last one?
Huh? We didn't, but we're going to need this to do the last one anyway. So let's just start this. So P stands for parentheses. E stands for exponents. M stands for multiplication. D stands for division. A stands for addition. S stands for subtraction. So the order of operations go, you want to compute in this order if ambiguous. And so we'd use these to make things not ambiguous. If I want you to do something first, I'll put that in parentheses. So you'll apply parentheses first, exponents come second, multiplication and division come third, apply left to right if both show up. And division and subtraction also have the same order. They come fourth, and you apply left to right if both show up. A lot of people always forget this rule. Like both of them are there. You can't just randomly pick and choose who you want to do first. You would apply them left to right. Brings us to example E. Not a terribly crazy example, but just a segue nicely into this. How would we do that? Just read the subtraction. So you see that, your eye should immediately hover to the parentheses. So you want to compute what's in the parentheses. Now what's in the parentheses, there's another parentheses. So you want to evaluate the inner parentheses first. You go to the innermost parenthesis is where your eye should start to hover. So you would essentially leave everything alone and deal with those parentheses first. That would be the first step. And then, now you want to apply the distributive law. Now we can still simplify in the parentheses here. It's minus x minus 4. By combining like terms. Now we can apply the distributive law. Minus 8. Now we can combine like terms. So that'll be that. So that's how you add and subtract things. What about multiplying things? Be multiplied terms. This one's actually a little bit worse. To multiply two expressions, take each term in one expression and multiply all terms in the other. Combine like terms afterwards. That's the rule. That's how we provide for multiplication. Let's do some examples. We got one. How do we do this one? FOIL, right? So whenever you have a binomial, two binomials, we call it FOIL. But what that really means is that the three, I'm going to take each term here and multiply each term there. Then I'm going to take the next term here, multiply every term there. I'm going to multiply out all the terms. Now, it turns out the order, and if you do it this way, what you end up doing is multiplying the two first terms, then the, I'll just do it and then I'll talk about where the expression FOIL comes from. But after doing that, so you'll take the 3x and you're going to multiply everybody. So it's 3x times x squared. 3x squared. 3 times minus 5 minus 15x. So you take this guy, multiply everybody in that parenthesis. Now you move to the next guy and multiply everybody. Combine like terms afterwards. 15 plus 2 minus 1 plus 2. Now you'll notice that people remember this by saying FOIL. You multiply the first terms, multiply the outer terms, multiply the inner terms, then multiply the last terms. So that's what FOIL means. If both expressions are binomials, this leads to FOIL, which means you multiply the first terms, the outer terms, the inner terms, and then the last terms. And then you combine. So ordinarily though, FOIL wouldn't apply here because now the mnemonic just breaks down. So you might like referring to it as this, but it's kind of a limited way to look at it. It only deals with one case. This is how you want to think about multiplication in general. Just take everyone in one set of parentheses, multiply every single person in the other set of parentheses. So what would this look like? All right, so start with the x, multiply literally everybody. It doesn't matter how many people are there, multiply everybody by x. So multiply this by x, that by x, that by x. Right? Once you've exhausted all the people, to the next guy. Now I'm going to multiply everybody over there by 1. So it's going to just so you end up with getting a list that long. And now you're going to combine like terms. You're going to have the x cubed. We have 2x squared plus x squared, that's 3x squared. We have 3x plus 2x, that's 5x. And we have that's how we multiply. So squares of binomials and squares. So this is just me wanting to remind you that a plus b all squared is equal to a squared plus 2ab plus b squared. And of course, we got to that by applying our multiplication rule. So I take the a, multiply everybody, so I get a squared plus ab. I take the b, multiply everybody, I get the ab plus b squared. These two combine, so that gives us plus 2ab. With that expression. A similar thing would happen if you have a negative sign in the middle. And these expressions here, we might call these perfect squares. So a lot of times you want to factor, someone might factor something and say, oh, I'm factoring this way because it's a perfect square. This is kind of what they mean, is because they see that it's coming from here. And do I have an example of that? Well, I can kind of, so one takeaway. When factoring, you can notice something is a perfect square. And we'll talk about this later on when we start to do something called completing the square. It's a perfect square if the constant term is the square of 1/2 the middle term. Example, you might see the expression x squared plus 6x plus 9. And you can notice that what this is x squared plus 6x plus 3 squared. And the 3 happens to be 1/2 of 6. So whenever you have such an expression, you can know that it will automatically factor into the guy on the inside. That's going to be the factor. So it's something you might notice every now and then. So we're kind of going through a bunch of things that were on the quiz now. I want to expand. That clock is like an hour fast. I wonder why it's an hour fast. Daylight savings time was a while ago. Anyway, what do those expand to? What is this one? This squared, this times 2, and then that squared. This one.
4y squared.
4y squared.
Oh, that's 4y. Plus 1.
Plus 1.
Difference of two squares. turns out if you expand something like a minus b times a plus b by doing the whole FOIL thing, the a squared plus ab minus ab plus minus b squared. Realize those kill each other, you get a squared minus b squared. Thus, we have the fact that a squared minus b squared is just this guy. This is called the difference of squares formula. So if ever I'm doing something and I say difference of squares, I'm talking about this formula. And note a, b can be any expressions here. So let's do some examples. This one's not on the handout. I'm just put it in there. Factor the first one.
Negative t plus 5 and 2 plus 5.
So the first thing to realize, yes, is of course that 25, you can write it as a square. So this would be 5 squared minus t squared. So now you can think of this as the a, that as the b. So your a is 5, and your b is t. And so now you can apply that formula. So what would we get here?
5 minus t, 5 plus.
That would be the factor. How do you expand that? Yeah, realize that this would become 2x squared minus 5 squared. Right? Yes, you could actually FOIL it out, but sometimes you want to get to a calculation quicker. And if you happen to notice, these are really just the same numbers, just the middle sign is different. It's actually, you can expand it, it'll look like a difference of squares when you do. So this would be 4x squared minus 25. So this isn't in your, how would you factor that? This is squared.
Factor x squared out.
You could factor x squared out. So that's 25x squared y squared minus 4z 6. Five xy minus 2z, yeah. What do you mean, yeah? Are you done? Is that it?
Oh yeah, and then 5xy plus 2.
So that's how it would factor. Because you would look at this guy as this is 5xy all squared minus this would be 2z cubed all squared. So that's the difference of squares. So your a is like this, your b is like that. Plug into that formula, you get this. The point is, difference of squares are going to show up in weird places. You should always be looking out for them. And things might look messy. I mean, this isn't even that scary, but you should be able to recognize something like a difference of squares, no matter what the things look like, by realizing if there are two things, difference of squares is always something you're looking for, because they will show up a lot. I mentioned this also. Some difference of cubes. Not as common as difference of squares, but common enough to mention, I guess. These also hold. If these are both cubed, that actually factors into this. And this one factors into that. There's no 2 in the front of this. That sometimes someone mess up with that. I believe it's example A. So you get x cubed plus 8 and you have to factor that. What would it look like? If you had to expand x minus 1, x squared plus x plus 1, what would that look like? What does that factor into? Right, so you're seeing that this, you can think of it as that. And so now, parentheses x plus 2.
Yeah, parentheses x squared minus 2x plus 2 squared, which is 4 plus 4.
That's how you factor that expression. See that how you expand it.
Distribute the x in a thing and negative 1
Okay, so what would you get?
x squared plus x plus x minus x squared minus x minus 1.
In other words, x squared cubed minus 1. Yeah. By applying this thing. This fits on top of that, which fits on top of that. So these rules just kind of give you shortcuts. Yes, you can expand, but if you notice this pattern, you can take advantage of it and not waste any time having to combine like terms. You can just understand, oh, that looks like the difference of cubes. It expands like this. So now we're going to talk about factoring. Super important. And this is, as I mentioned before, the opposite of expanding. So if I had a squared minus b squared equals a minus b times a plus b. We say going from this to that is called factoring. Basically, you're moving from a sum of terms to a product of terms, or a product of expressions, right? Ever so often, it'll be necessary for us to do that to simplify certain things. Going the other way is called expanding. So if you go from a multiplication of expressions to just a sum of terms, that's called expanding. If you go in the other way, it's called factoring. Now, you'll have to factor all sorts of things for all sorts of reasons, and you need to know how to do that. So we're going to start from scratch and figure out how to factor. So in the notes, you'll see there's a general approach to factoring. So if I give you random things to factor, you shouldn't be lost and not know what to do. There are steps that you follow in certain orders. We'll look at the general approach. These will show you the principles you need to apply when factoring any random thing. Step one. If a GCD not equal 1 exists, factor it out. It's kind of like what you were saying earlier about factoring out the x squared because it was common to both. So GCD, by the way, GCD stands for general greatest common factor. By the way, when you have something in factored form, a minus b times a plus b, this is called the factored form. You might refer to each one of the things in parentheses as a factor in the expression. So in general, if you have a multiplication, each thing you can call it a factor of that multiplication. And if there's something like that, that's a factor in everything, every term, you call that a greatest common. Yeah.
Is GCD and what's GCF?
Oh, I do mean F. This is greatest common factor. So it was like the x squared. Do I do examples now or at the bottom? Let's do the examples as we move along. I put them all after the list, but let's do it as we move along. Okay, so let's talk about Gcf factoring. So example. And by step one, I mean you should try to do this first. It's the first thing you want to look for, factoring any random thing. So for example, factor 4x squared plus 4. So we'll do that, and then I'll make some comments about Gcf factoring that you probably never thought of before, or maybe you thought of it once. I want to make sure you remind you of these ideas, because when it comes down to it, it can mess you up. Okay, so how do we factor this?
Factor 4.
Right, 4 is the common factor, it's a common term. Sure. Is that 4 itself is something that's common, it's in everyone. So this is the GCF, and we can factor it out. And this is what we mean by factor it out. Talk more specifically about what that means in a little bit. Was that cube or a square? Maybe I could leave it as a cube. See another example. Okay, what do you see here? Right, 2 is a common factor. See, a 4 is actually a 2 times a 2. What else?
X1, X5.
X is a common factor. Notice that there's an X in everything, in every single term. Remember, a term is just a bunch of a product of expressions. There's also a Y in everything. So this means you have a GCF. There are terms that are in everything, factors. So what would you pull out?
So that's why.
2xy. I'm going to talk about y to xy soon. So the goal here is to factor out lowest, smallest powers. Pay attention to that. I know you guys probably instinctively do that, but there are times when you have to consciously think about that. 2 here has the power 1. 2 here has the power 2. This is 2 to the 2. 2 here also has the power 1. So the powers are 1, 2, and 1. You pull out the lowest powers, it happens to be 1 in this case. You pull out a 2 to the 1. Here we have an x to the second power, x to the first power, x to the second power. The first power is the smallest power, therefore I put out x to the 1. Here y is in everyone. Y is to the first power, here's the second power, here's the second power. 1 is the lowest power, I pull out y to the 1. Now what do we have left inside?
X plus Y.
Right, so now you pretty much go and you take out the factors that you already pulled out from the original. So there was a 2, I took out the 2, so he's not there anymore. Okay, so you move on. There were 2 factors of x, I took out 1 factor of x, so there's 1 factor of x left. Right? There's 1 factor of y, I took that out, so that's gone. Move to the next term. 4, there were 2 factors of 2, I took out 1 factor of 2, there's 1 factor of 2 left. Here's x, there's 1 factor, I took out 1 factor, so that's gone. There are 2 factors of y, I took out 1 factor of y, so there's 1 left. Move on. Look at this. There was 1 factor of 2, I took that out, so that's gone. There were 2 factors of x, I took out 1 factor of x, so there's 1 factor of x left. There were 2 factors of y, I took out 1 factor of y, so there's 1 factor of y left. So that would be the factor expression. Now, sometimes things can get a little bit complicated. For example, let's say, okay, so this is another example, but I want to give you something like that on this. There were a bunch of factoring examples on the quiz, but I didn't put this one. Okay. Don't look. The first thing. This. Okay, factor. What do we do here? Okay, there's a 2 in everyone, you can take out a 2. There's also an x in everyone, you can take out the x. What power do we take out? No. This is one of the things where I talk about, you think you know, but you probably don't know. pay attention, be very specific. You always pull out the lowest power, always the lowest power. What factor of x do I pull out? Negative 1/2. It is the smallest power of x. Okay, so in that case you pull out the negative 1/2. Now, what do I have left inside? Now here's what do I have left inside? Let's go with that, then we'll talk about where that comes from. Huh?
X
What do we have?
X to the negative 1.
X to the minus 1?
Plus 2. X. No, so it's 2.
Just 2.
Plus 1.
Plus 1. Seems legit.
Oh, hell no.
Just like shaking your very quietly. No. When you pull out a part, do you realize what you're doing? Like what it means to have something left over on the inside? Remainder in what sense? Okay, so if I ask you to factor this, what would you do?
You got an X squared.
We got X.
X squared, again, lowest power, right? So now the power we're getting stuck on is what is left on the inside. What is left on the inside? Subtract, that's the thing. The power you pull out is subtracted from all the powers on the inside. So what's left over is 5 minus 2. 2 minus 2. Now instinctively you just know you factor out x squared, you get an x cubed plus 1 left over. But why is it x cubed plus 1? Because the thing you move out, you have to subtract it. Because when you multiply, the laws of exponents say you have to add it back to get the original. So whenever you pull out a power, you're subtracting that power from the inside. So this becomes x cubed. This becomes x to the 0, which we know is 1. So that ends up being x cubed plus 1. Now, you normally jump straight to here, but you have to understand how did you get there? Sometimes you have to think about that. Whatever power you pull out, you always pull out the lowest power. To determine what is left over, you subtract the power that you pull out. Now that we know that, what's left over?
X squared plus
X squared, right? But let me write that out. In other words, the 2, I just had the first power, so now I'm left with 2 to the 0. But I have x to the 3 over 2 minus 1 over 2. Plus 2x to the 1/2 minus a minus 1/2. Plus x to the minus 1/2 minus a minus 1/2. Right? That's what you're going to have left on the inside. So now, computing this is where he got the 2 from. You're left with an x squared. Right? Not minus 1, so it'd be a square. Plus 2, a half minus a minus a half is what?
1.
1, so that's just x to the 1 power. Minus half minus a minus a half is
0.
0, x to the 0 is?
1.
So that's a 1. Can we factor that?
X plus 1, X plus 1.
Right, that's a perfect square. This is half of that squared. So that's the factor. Perfect square. So the reason why I'm going through the preliminaries, I know there are a lot of things that you guys do instinctively, but you don't really get why you're doing it. So when the problem becomes slightly more complicated, all of a sudden things get messed up. Think very carefully about what you're doing. So make sure you're paying attention. Now, if, so whenever I give you a random thing to factor, the first thing you look for is Gcf Factor. If you're looking for something that is in everyone, you factor out the lowest powers always, factor out the lowest powers. No matter how ugly the powers look, even if they're crazy, it does not matter. Figure out who's the smallest guy, factor that out. To figure out if it's complicated, to figure out who's left over on the inside, subtract the power that you factored out so that you don't mess up. Sometimes if it's whole numbers, it's very clear what it should be, but as soon as anything slight tweak is made, it can get confusing. So just really be aware of the steps that you're taking in order to do something. Factor out the lowest power, subtract that power to figure out what's left over. Were you raising your hand or?
No,
Just
just
stretching?
stretching. I have a
Um,
question.
yes.
When you have a negative exponent, don't you have to make it positive?
No.
Like when do you do that?
So I know in like algebra and pre-cal they tell you we don't like negative powers. In calculus we don't care. Or things like radicals in the denominator, we also don't care in general. So I know sometimes if you had an answer like 1 over radical 2, oh, you can't do that, you have to do this. You have to rationalize and write the answer as radical 2 over 2. In calculus, you don't care. A lot of times they said to do that because they wanted you to get familiar with the operations and manipulating things. But in calculus in general, you're not going to care. The only time where this would be an issue, only worry about. So if I'm asking you a question and I ask you for the answer, I wouldn't care if you leave a negative sign there, but only worry about this in multiple choice problems. Make sure you choose the right answer. So in a multiple choice problem, whoever typed up the exam, they might choose to put a negative power, but they might choose to write it with the positive power. You should be able to recognize which is which. So if on your paper you see this answer, but in the answer choices, it's the answer with the X in the bottom, you should write, oh, that's the same as my answer. You should know to circle that. As opposed to, so just be prepared. So you should know how to manipulate these things, just in case the answer choices puts the answer in a different form than what your working was. But beyond that, no one cares. Calculus and above, we don't care. We're not scared by things that look ugly. Step 2. So we're still in the general approach, step 2. This is basically to take advantage of formulas. I.e., if you're asked to factor an expression with 2 terms, check if it's difference of squares or difference of cubes. All right, we went over this already, so I'm not going to go over it again. Or sum of cubes. So if I ask you to factor something, it's a random thing. First thing to look for, are there any common terms? Pull them out. Next thing you look for, if there are 2 things, try to see, is it a difference of squares? Is it a difference of cubes? Is it a sum of cubes? These are the first 2 things you should think of. Right? Trying to get the GCF out, and then try to see if there's a nice formula that helps you to factor something. And okay, so I didn't give any examples on that. And, okay, so we'll move on to the next one. Step 5. If 3 terms. Check if it's a perfect square. this. We'll talk about these next time.
Did we get to the 2.1? Or is this just?
Oh, we're still in chapter 0.
So the homework?
No homework.
Okay.
But I would, I'm going to test you on algebra again. The quiz won't be as long as this first one, but I'm going to test you with some of this stuff again. So go over the quiz 1, especially in recitation. I'll probably test you. Technically it's prerequisite material. We're going over it slowly to pick up any nuances that you might not have picked up before, but technically everything I'm doing right now is stuff that I expect you to already know. Yes, that's that there are 3 terms. Four or more trifactorized grouping. And we'll also do this next time. And I actually have some examples on that. So you can actually try the rest of them and see if you can actually do them. And step 5. Always check if resulting factors can be factored further. Okay. So like here, for example, this problem started out with you factoring out the GCF, but you realize that the thing that appeared could have been factored further. So you always want to check for that. But that's basically, so these we'll talk about in detail next time, make sure we all remember how to do that. I highly recommend you read through the notes and try to do them on your own. But in general, this is how you approach a factoring problem. First thing you look for, is there a GCF? No. Does it have 2 terms? No. Does it have 3 terms? No. Does it have 4 terms? No. You literally go down in this, through these steps in your head, and you apply the rules for each of them. How to do these, we'll talk about next time. And I think, what time is it? Yeah, so we're actually done with me. What you can do is go over, I don't know what they have time for recitation because I don't really have control over that. But probably go over the quiz, make sure you guys understand that stuff. I'll probably give you a quiz on similar material next time. And we should be getting into the actual syllabus next time as well. I think that's it. So I think the second section is in the same classroom at 1:50. Any questions before we go? No, it's on Blackboard. So if you go into your Blackboard in the right menu bar, there's a section that says My MATLAB homework or purchase My MATLAB. There's a tab there. Just click on that, there should be instructions. No, but you should be studying. Yeah, I would go over all the things you saw in quiz 1. Right, so quiz 1 asks you a bunch of things like code, expand and simplify, factor this, solve this equation, right? Find the equivalent. Well, no, I didn't grade it yet. So. But it's online, it's on Blackboard. I mentioned that. Okay.
My head is hurting. I'm like falling asleep.